Metalloborane. Metalloborane are metal-containing boron classes. It can be formed by two ways. The first one is by complexometry reaction, where metals are being appended by borohydride ions through hydrogen bridges. An example will be aluminum triborohydride, where aluminum forms coordination bond with 3 borohydride ions. Each ligand chelate with the metal in 2 different sites, as you can see in the red circles. Another example is zirconium tetraborohydride. Another example is zirconium tetraborohydride, where zirconium oxidation states is +4. Again, the red circle shows the bonding between zirconium ion and the ligands. Metalloborane can be formed by direct Metalloborane can be formed by direct metal-boron bonding as well. This is more common and more robust compared to the other one. Metallocarbons. Metallocarbons are metal with carbon-based clusters, and they can be structurally simple or complex. Most of them are metal-carbon direct bonding, and they can form similar conformation with boron structural pattern. These are the examples here given. This is the simple one, which is actually a Grignard reagent. It is a methyl magnesium bromide, and this is another catalyst actually similar to Grignard reagent, and it is called DIBA. It is also an aluminium. It is also a carbon base. From PSEPT, there are 3 main types of polyhedron. The first one is closo, which is a polyhedron with n vertices. For example, here a diagram given is a square bipyramidal with 6 vertices. And the next one is nido polyhedron, which consists of n+1 vertex of closo polyhedron with 1 missing vertex. So the structure will look like a square bipyramidal. The next one is arachno polyhedron, which is n+2 vertex closo polyhedron with 2 missing vertices. Once another vertex is missing, we can get the structure trigonal pyramidal. These are other types of polyhedrons. There are other types of polyhedron listed here as well. And this is actually a simple table of PSEPT.
This is the example of one of the metalloboron, which is closometalloborane prepared by interaction of acidic hydrogens in sodium borohydride with trimethyl aluminium. The equation is shown in the pictures below. For the synthesis of metalloboranes, the most general route involves the reaction of mononuclear coordination complex with a boron anion, or direct reaction of neutral borane with various reagents. The second is more complex and therefore has a low yield. For the reaction of mononuclear coordination complex with a boron anion, the synthesis can start with a preformed borane anion such as closoborohydride, nidoborohydride, arachidonoborohydride. Many of these reactions occur rapidly in CH2Cl2 solutions at room temperature or lower. This is the example of the synthesis of borohydride anion to form the arachidonmetalloborane and numerous metalloborane products containing 4 to 10 boron atoms. Next, for the direct reaction of neutral borane with various reagents, it can be divided into boron as a simple 2-electron ligand and borane as a Bronsted acid. For boron as a simple 2-electron ligand, the nido borohydride displaces other ligands from their complexes by acting itself as a Lewis base via interaction with the vessel boron-boron 2 electron bond, and the example of equation is shown below. For the borane as the Bronsted acid, boranes can be deprotonated by metal alkyl and other reagents to give a variety of metalloborane structures types. And this also shows the examples of the synthesis of the metalloboranes.
Metalloboranes is usually in crystalline form. It is a stable compound as compared to boron hydrides. The free boron hydride is not stable because of its lowest energy structure. Metalloboranes has high thermal and oxidative stability. In bonding properties, it is linked by 3 center 2 electron bonds as shown in the figure below. The red circle in the figure shows the 3 center 2 electron bonds in which 3 atoms share 2 electrons. This is another example of metalloboranes, in which it is a Lewis-based adduct. It has 2 bridging hydrogen atoms between 3 boron atoms, which shown in yellow line. It has 2 hydrogen atoms, which is pink in color, that bonded to boron are pointed directly at the chromium atoms, enable triborohydrate bond to the chromium atom through 2-3 center 2 electron chromium hydrogen boron bonds, which shown in red line. There are several applications of metalloboranes. One of it is act as fogging agents in direct positive emulsions. The advantages are metalloboranes are effective and not affected by pH. It shows good fogging properties under both acid and alkaline conditions. Metalloboranes has high density hydrogen storage. With the advantages, the transition metals do not aggregate on the metallocarborane. In high hydrogen storage capacity, metalloboranes able to form stable covalently bonded molecular network and able to mimic the bonding structure of carbon. Metalloboranes able to link into metal organic frameworks. Since the borane 6-atom ring has identical bonding properties as carbon rings, thus metalloboranes able to absorb hydrogen via Kubar's interaction as well as van der Waals interaction. 6 electrons must be transferred into the ring in order to stabilize planar hexaborate. The figure below shows planar metalloboranes. Next, we will going to discuss.
Let's have a look on a very basic fullerene model, which make up the metallo-carbon compounds. Fullerene model is a molecule of carbon in the form of circle ball shape, which exhibit 12 pentagons and 20 hexagons. The finalized fullerenes can be divided into 2 classes, which are exohedral fullerenes with substituents outside the cage, and also endohedral fullerenes with thread molecules inside the cage. Fullerene able to undergo series of addition reactions, oxidation, hydrogenation, and pericyclic reactions. When added as a ligand, the C60 will behave primarily as an electron-deficient alkene. Next, metallofullerene. Metallofullerene is a molecule composed of a metal atom trapped inside a fullerene cage. They have unique electronic properties and structures which are not expected for antifullerenes. Metallofullerene was first generated by the supersonic cluster beam technique in the gas phase by Smalley and co-workers. The simple metallofullerenes consist of a fullerene cage with 1 or 2 metal atoms trapped inside. The atoms that encapsulated inside the cage was indicated by the 8 symbol in the formula. Normally, group 3 elements, group 2 elements, and the most of the lanthanides are preferentially encapsulated in the fullerene cage. The next slide shows some of the examples of the metallofullerenes. In the slide here, we can see that the calcium Lanthanum, cerium, and erbium can be encapsulated in the cage of fullerene to form metallofullerene.
Application of metallofullerene. It has a non-toxicity of carbon case made. Metallofullerene-based drug potentially feasible for medicinal application. It has a biodistribution of metallofullerene have indicated that this carbon case compound primarily localized in liver and clear only very slowly. It is up to 40 times better as contrast agent in magnetic resonance imaging MRI scan for diagnostic imaging. Below was the picture of metallofullerene based on magnetic resonance imaging. However, gadolinium metallofuranol suffer from serious aggregation in pH below 9 aqueous solution and are difficult to modify chemically. Thus, synthesis and characterization of a new water-soluble endohedral metallofullerene, abbreviated as AAD, EMF was reported. A is GD metallofuranol and B is AAD EMF. The synthesis of AAD EMF. First, briefly, a solution was prepared by dissolving sodium hydroxide in beta-aniline in the ionized water, then ethanol was added. Next, the resulting solution was added dropwise to 25 ml gadolinium in toluene solution under stirring condition, and the solution was stirred at 80 degrees C for 25 hours until the organic layer become completely colorless. Below was the reaction of gadolinium C82 with the beta-alanine is shown below. After the reaction of aqueous layer was separated from organic layer, concentrated, and then chromatographed on the gel column with distilled water as eluent. The sample was collected under the pH 6 to 7 as a brown solution.